Again, welcome to another lectures on data structure. This is CUS 11226 class, a data structure class. And our topic today is trees. Today we are going to learn the basic concept of trees. The lecture slides was again developed from this textbook named Java Foundations, Introduction to Program Design and Data Structures. So we will using studying data structure using Java language in these lectures. So again, trees, our main objective is we will go through a trees as a data structure. We will learn some tree terminologies, also in the implementation concept. Again, this will be lectures. I'm not going to introduce coding here for now. That will be a different lectures. And also tree transversals and also expression trees. So everything here again is theory. So the first, we will go through the definition of a trees. So I'm going to read the slides here and then we break it down. So a tree is a nonlinear data structure. I would say a tree is a nonlinear data structure in which elements are organized into a hierarchy. So a tree comprises of a set of nodes in which the elements are stored and edges connect one node to another. Each node is located on a particular level and there's only one root node in a tree. So what we mean here is that tree is a nonlinear data structure, which means the data is not organized linearly or sequential, such as a queue and a stack. We know queue is a linear because data go through sequentially. Through the back comes from the front, first in, first out. Stack is linear, also sequential. Data goes through in from the top and out from the top. But in trees, it's hierarchy in the form that we have the root of the tree at the top and the leaves are down. And we'll see a diagram, maybe the diagram will again give us the whole concept. So here we want to know some few terminologies in a trees data structure. So what is a node? Normally when we want to implement a data structure as a dynamic implementation, which means memory will be allocated to the system during the running process or during the execution time. So the size doesn't matter. So here we need to use the node. So the node normally will consist of the information and the address of the node that is pointed to. We talk about a linked list, and linked list we use the single linked list, which means one node will carry the address of the next node. We also can use the double linked list, which means one node will have two addresses, the address to the previous node and address to the next node. And we'll see the concept of trees here. So we know what is a node. Again, node consists of info and address. And the concept of node is like a pointers in C++. It will carry its data, but at the same time, it will carry address that is point to. So a node can have one parent in terms of a trace, but can have as many children. The root of the node may not have a parent because that's the beginning, the starting of the tree. And the leaves of the tree doesn't have no children. That's the end of the end. So we call each of the elements in the tree as a node. So here we say a node that has no children is called a leaf node. And again, next slides we will see the example of a diagram of a tree and we may understand it more detail. So we have the child and also the parent and also a subtree. Subtree is just a part of the tree structure. And also the path will be from one node to another. We have to go through a path. And I will explain this more detail in the diagram, which is this. So this is the root of the node. So node A is the root. That's the beginning. A root node is only one and it does not have a parent. So it can go up. That's the beginning. The root always have children. When a root doesn't have no children, it means the tree consists of only one node. So in this diagram here, the root A have 4 children, B, C, D. And B is internal node because it have a parent and also it has children. So it's within internal node. So B children are F and G. And G also have 2 children, L and M. So G also is internal node. F is a leaf, it doesn't have no children. So now what is a path? A path is how we traverse through the tree. So for example, if I want to move from A to N, I would say my path will be A, D, I to N. We can see there's a line. If I go through A, D, H is a leaf. I can't go down to N. So we have to follow the edge. Again, the line is called the edge. And also, as we said, the leaf is the node with no children. So a path is how we travel through or traverse through the tree. So if I want to go to M, I can't go through A, C. C will be the end because C is a leaf. But maybe I have to go through A and B. B, I can't go F, I will go to G. Then G, I can go to M. Or if it's L, then L. So nodes can also be reached by following the path, as we said earlier, from a particular, let's say I'm moving from D to O. So my path will be from D. There's an edge between D and I, so I'll go through I, and there's an edge between I and O, so I'll go. So from D to O, the path will be D, I, O. And that's what we mean, the path. Also, what is a level? The level is each level. The level is each of the trees. So for example, in hierarchy, the steps. So for example, A will be level 0. Then when I move to the next step, B, C, D will be level 1. Then F, G, H, I, J, K level 2. Then L, M, N, O, P is level 3. So from the root A to the longest leaf, which is the longest tree, which can be P, O, N, L, or M, we give us the height of the tree. So the height of the tree, the level start from 0, then it will be 0 plus the longest level from the root to the leaf. Why I say the longest level, for example, from A to F, F is a leaf, but F is in level 2. But L is a leaf, is in level 3. So the height of a tree will be from the root to the longest level. So this is a good example. So what is a level? A is level 0, level 1, level 2, level 3. Again, each step. And so to calculate the height of this tree, the answer will be 4, which will be the number of levels plus 1. So sometimes we may classify trees. And how do we classify trees? Most of the time it's based on the number of children the trees have. For example, if a tree have at most it can have only 2 children, then we call it a binary tree. If you can have at most 3 children, then it's called ternary tree. So this normally is referred to the order of the tree. A general tree may have no limit pertaining to the number of children. There's no limit for it. So what is a balanced tree? A balanced tree is a tree that the level are in the same, the leaves are in the same level. The leaves are in the same level or one above. So we can see that this first tree on the left is a balanced tree. Why? The levels are on the same, the leaves are on the same level and only one above. So here we have 1 leaf above. Now, if we have 2 leaves above, then it's not balanced. In this case, this tree is not balanced, the one on the right, because we have 1 leaf here, and then we have to move 2 up to see another leaf. Only 1 up is balanced. Also, we have what we call the full and also complete trees. A full tree normally It's a tree that all the leaves are in the same level. So example here, A is not a balance. A is a balanced tree, but it's not a full tree. C is the full tree because we can see all the levels, all the trees and the leaves are in the same level. This is balanced, B is balanced, and A also is balanced. So only C is a full tree. A full tree again or a complete tree is a tree that all the leaves are in the same level or one above. So a complete tree can be a balanced tree also. So this is a complete tree. A, B, C, they are all complete trees. A balance of full tree. But the full trees cannot be also, sometimes it can be a balance, but all the leaves have to be in the same level. In a balance, we say all the leaves have to be in the same level, and another option, one up. So implementing trees is the same concept as stack and queue. If we are using dynamic implementation, that is the linked list, then which means we may have a class name link node or a node. Then this class node will be used by the binary tree implementation, or let's call it binary tree class, to create a node, same as linked list, use stack using a linked list. Array is possible, but the problem is that with array, if we know the number of children, or if the number of children are very small, let's say the at most is 2, we can use array implementation. But if there is a general tree or the number of children is 4, 5 at most, sometimes we may going to waste a lot of memory, because anytime we create one node, we have to leave 4 space for all the children. So if the node have only one child, then we use only one, then we still have to leave the 3 down, then we go to the next level. But with dynamic implementation using node, that's more efficient. So example they gave you, let's say if I'm in, for any element stored in position n, let's say position n is 2, this means if it's a binary, I will have 2 times 2 plus 1, then 2 times n plus 1, which means if this is 5, this will be 6. If this is 7, this will be 8, based on the n value. So this can be our left and right child. So the left child will be 2n plus 1, the right child will be 2 times n plus 1. So this is a very simple example here to see how array implementation works. So the root always should be number 1. So I have my root as index 0. You have 2 children. This is a binary, so at most is 2 children. So I leave the 2 space, 1 and 2, which is B and C, the children. Then this is again, at most is 2, so the implementation is kind of efficient. Now I move to D. D have 1 child. So which means I have to prepare, we can see the C, A, B, and C. Then we see the B went to D and E. Then we see that D will go to F. But also E is the N. But the reason why we leave 2 space here is because of C. Because C can have at most 2 children. It's not a leaf yet. Then we can continue with this. E also supposed to have 2 children, so we have to leave reserve of 2 space. So this make array implementation not too efficient. We have a simulated child links here. Again, the same concept. So we can see A, B, and C, the 2 children. We have to leave 2 spaces for all the, this is binary. 2 space means the 2 children. So next step is the tree traversals. In a linear structure, such as queue or stack, we can push, pull, or insert or remove item from the queue or the stack against linear. So in stack, last in, first out, so the top have to come out first. In queue, first in, first out. So if you're in the queue first, you come out there, the one at the back will move forward. So you can see that it's sequential. But with tree transversals, we have 4 different methods. One is called the in post, another is pre-post, another is post. Sorry for the name. The tree transversals, one is called the in order, then pre-order, then post-order, then the level order, which are 4. So that's what we say here. For nonlinear structure like tree, the possibilities are more interesting. We have at least 4 ways. Then let's look at the 4 classic ways of transversing the nodes of a tree. So here we see the pre-order. Now the name is based on when we visit the root. So we see pre-order means the root is first, so it's pre. Then always we go left before right. Now in order means it's within. So left, then the root, then the right. Post order means we go to the left and right, then after, before we go to the root. So post order. Level order means we go through all the nodes one level at a time. And we will see an example here. So here we have a tree here, which is A is the root. We have 2 children, B and C. And C is a leaf, but B also have 2 children, which is D and E. So D and E and C are leaves. Now, how do we transverse through this? Let's go through the pre-order. Pre-order, we say we have to go to the root first. So you can see it's A first. Then we go to the leftmost. So we go to B, then we go to D, the leftmost. Then after we finish with all the left, at the down, we start with the right, E. Then if there's another right, we move up. Then we go to the right section of the subtree, which is C. So here we can see that we have A, the root, then B, D, E, then C. Now, in order means we should go through the left first, then the root. But since the previous pre-order, we start at the top. So the left, we don't want to start from the leftmost D, which is not efficient. So we start with the leftmost from B, D, the small, we keep going. But in order, we start with the left first. So we start at the bottom. Left is D, B. We can't go the root yet till we finish the left subtree. So the next we go to the E. So we have D, B, E, then A and C. Post order to the same thing, we still go left first. So we go through D, E, B, then C and A. Then level order means one level at a time from the top. So A is level 0, then B and C level 1. So it will be A, B, C, then D, E. So those again are the 4 major classic tree transversals techniques. So this is the pseudocode. Pre-order means visit the node first, which is the root, then use the recursive function. We call the method transverse through the left first, then through the right. In order means transverse the left, then visit the node, which is the root, then transverse through the right. Then post order means transverse through the left first, then the right, then visit the node. Then the level order is more complicated in terms of the coding, but it requires the use of extra structures such as queue and or list to create the necessary order. And we may see the code again in our next class. So this is the binary tree ADT. Here we have the operations. Get root means we want to know the info in the root. We can also check if the tree is empty. The size will give us the number of nodes in the tree. Then contains, we can check if a specific value or character or something it contains. Then find means searching for an item. Then we have the toString, then iterator, in order, pre-order, post-order, and level order. So this is the binary tree, again, ADT, and the description is on the right side. You can take your time to go through it. And this will be my class diagram, and this is interface. So we have binary tree ADT and all the possible methods. Now we can also use the tree, especially binary tree, to find an expression or to verify an expression. So here we have 5 minus 3 times 4 plus 9. So I want to check if this expression is correct. So I'll start with the down, 5 and 3. The operator always will be our parent now. So we have a child 5 and 3 left and right. The parent is minus. Then when we get the answer here, you can see that this is like doing the parentheses. We are going to multiply the answer by 4. So that's why we have this 4. Then the answer we get, we are going to add it to 9. And that will be the end. So let's look at an example that creates an expression tree from postfix expression and then evaluate it. This example will be discussed during the lab work or during the lectures on the coding. So this example given to us, we can see that from here, we can build an expression tree stack. So first, as we said earlier, implementing this, we need to use a stack and queue. So first we push a new expression tree, and it's 5, no, no. So that means we have only one node, which is 5. Then next we push new expression, 3, no, no. So we have the third one. Now, since we have 2 nodes, we can look for the operation. So we say operator 2, we assign pop to operator 2, pop to operator 1. Then we push new expression, minus operator 1 and 2. So what this will do is that it's going to find the difference of the 2 values. Then next we push number 4, new expression. Then we assign pop to operator 2 and operator 3. Check. Then we push a new item again, 9. And the same thing, we pop it also with the plus. So this is all the implementation for the binary tree. We have the binary tree ADT. Then we have the binary tree node, which will be used again by the binary tree implementation. And implementing a binary tree with links is very, very important. So we can have our link binary tree class, which will hold the references to the roots. Then we have the binary tree node. This will be the class that will create a node. Anytime we are inserting an item, we have to create the node dynamically before we insert it. Again, this is where I'm going to end for these lectures. These lectures give us a basic concept of trees and the theory behind definitions, names, and also how the implementation will look like. Using a class diagram, we saw some of the operations we can do, and the instant variable. Mostly the instant, since this is a dynamic implementation using node, the instant variable will be our node properties. So again, wish everybody the best. Thank you. Bye.